Hello everyone. Okay, it's Monday and sorry. So let us start chapter 7, the new chapter. But this chapter introduces several techniques regarding the integration. So please listen carefully, and if you have any questions, please let me know. Okay. If you keep silent, then I cannot notice whether you know or you do not know certain topics or concepts. So if certain topic is not clear, then please let me know or you can email me. Okay. Okay, then let's just start chapter 7. Okay, the first thing we want to consider is the integration by parts, which is very, very important. Okay, so this section is very important. Okay, so please listen carefully. Okay, so every differentiation rule has a corresponding integration rule. For instance, the substitution rule for integration corresponds to the chain rule for differentiation. Now, previously in the differentiation, we learned some formula called the product rule, and the corresponding formula for the product rule will be the integration by parts. So the integration by parts comes from the some into the product rule. So what is the product rule? Given the product of two functions, say f and g, the derivative of this product will be fg prime plus gf prime. In other words, you need to differentiate each function one by one without touching the other, right? So we have a product of two functions, f and g. Its derivative, it will be f times the derivative of g plus the derivative of f multiplied by g unchanged, right? So this is the product rule. So that means the f times g will be the antiderivative of these two terms. So if I integrate f x g prime of x plus g of x f prime of x, then you will obtain an antiderivative. So fx times gx plus certain constant, right? So that will be the corresponding formula for the product rule. Now, when I look at this left-hand side, that is the integral of two terms. So that can be written as the sum of two integrals, the integration of f of x g prime of x dx plus the integral of f prime of x gx dx. So that sum of these two integral will be f of x times g of x plus a constant, right? Now, given this relation, if I move one of these two integrals to the other side, then we get a formula called the integration by parts. So, as I said, if you integrate these two terms, you get f of x times g of x. Of course, you need to add a constant. And then as I said, if you separate this integral and then if you move one of these two terms to the other side, then we get this formula, and that formula will be called the formula for integration by parts. And this is used in many applications. And whenever you integrate in many integral problems, except for very simple situations, you need to apply the integration by parts. So what is the point here? The point of the integration by parts is this. On the left hand side, I have g prime. Okay, so we have the differentiation, the derivative of g. Okay, so the differentiation is applied to g of x. And on the right hand side, what I have is f prime of x. That means we have the derivative of f. So on the left hand side, the differentiation is applied to gx. On the right hand side, the differentiation is applied to the other one, f. So given the integral of two functions, and if the integration is a little bit challenging, or if you cannot find certain appropriate way to integrate that function or product, then the integration by parts tells you that you can interpret one of these two functions as a g prime and the other one as f of x, and then apply the integration by parts so that the differentiation goes to f of x, not gx. And sometimes this integration by parts will help you in many problems in the integration. Okay. So here is some example. Suppose that I have a product of two functions. If I have only x, or if I have only sine x, then the integration will be simple. But now I have a product of two functions, and it is very difficult to find an antiderivative of x times sine of x. So we can apply the antiderivative, the integration by parts. So I can interpret x as f of x and sine x as a g prime of x. Usually, if you have a product of so some power of x multiplied by certain trigonometric sine x or cosine x, if you have such integrand, then usually you put this power of x as f of x and sine or cosine as g prime. That is usual trick. Okay, you can consider the other situation. I mean, you can call power of x as a g prime and sine x or cosine x as f of x. But if you do that, the power of x increases, and the problem, it, it becomes more complicated. But if you put power of x as f of x and sine or cosine as a g prime, as we did in example 1, then the beauty of this is that this power of x will decrease as you apply the integration by parts. Okay, so let's see what happens. So if I assume that x is f of x and sine x is g prime, then f prime, the derivative of f will be just 1. And if g prime is sine x, what will be cosine? What will be an antiderivative of sine? At this point, some people may answer that just the cosine x, but please be careful. If you differentiate cosine, you get negative sign. So an antiderivative of sine will be negative cosine, not cosine. So please be careful with this simple situation, simple result. And then what is the formula of the integration by parts? If I assume that f of x times sine x, if that corresponds to f of x times g prime of x, then the integration by parts tells you that that will be f of x times gx minus gx times f prime, in the integral of gx times f prime. Now, f of x, gx is negative cosine, minus, now gx is negative cosine, and what is f prime? F prime of x is 1. Okay? So you can write down 1 here, but multiplication by negative cosine x will give you just negative cosine. Okay? So negative cosine x is the integrand. So here I have two negatives. So they will make just one plus sign, and then you need to integrate cosine x. So in this integral, you need to find an antiderivative of cosine. What is it? Sine. So, so the result will be negative x cosine x plus sine x plus constant c. Now, actually in theory, as I said, the original formula for the integration by parts must add constant c here, right? But for simplicity, people usually omit these plus c, okay? And then you put the constant c only at the end. So at the end, you put constant c, but in between, you can omit this plus c here. Okay, so that's the usual notation for constant c. So even though you do not write down constant c in the middle of the calculation, you must add this plus c in the final answer. Otherwise, you will lose a certain point. Okay, so because we want to find this. So what is this? Find this. What is the meaning of this? That means we want to find an antiderivative of x sine x. So, so if you just answer negative x cosine x plus sine x only, then that is just one antiderivative. But we need to find, oops, find the general form. So the actual question is find a general form of an antiderivative of the integral. That is the formal question. So finding a single antiderivative is not sufficient. You need to add a constant c to describe all the possible antiderivatives of x times sine x. Anyway, I guess you are familiar with this one. But anyway, the point is this. If you have a product of two functions, and if it is not that straightforward to identify an antiderivative, you can think of the integration by parts. That means you need to put one of these two functions as f and the other one as a g prime. And usually, if a certain part of the antiderivative is a power of x or any polynomial, so power of x or a polynomial in x, then usually that part will be corresponding f of x, and the remaining part will be your g prime. Okay. Now, in case we have the same formula, we have the same integration by parts formula for definite integral. The only difference here is this one. Since we are integrating from, say, a to b, the formula for the integration by parts will be this. Okay. The integral of f times g prime from a to b will be this value minus the integral of g times f prime. As you know, this notation here means the value of this product at b minus the value of this product at a. So this is the formula for the integration by parts for definite integral. So here, let us look at this problem. We want to integrate arctangent of x from 0 to 1. Now, my integrand is only one function, single function. We have only one function. So then how can I find, how can I consider this? How can I apply the integration by parts if I have only a single function? As I said, the integration by parts considers the integration of a product of two functions. Now I have only a single function. So in this case, okay, even though you have a single function as your integrand, I can regard this integrand, the arctangent, as the product of two functions. One is definitely the arctangent, the other one is the constant 1. Okay, so if I introduce the constant 1 as my second function, you need to consider this 1 as your g prime. Please do not put this 1 as your f of x, but g prime. And arctangent will be your f of x. Then what is f prime? What is the derivative of the arctangent? 1 over 1 plus x squared. And if the derivative of a certain function g is 1, what will be g of x? Which function shall I differentiate to get 1 as the derivative? It will be x. So if I interpret this arctangent as arctangent times 1, then this problem will be f of x times g of x evaluated at 0 and 1 minus the integral of f prime, which is 1 over 1 plus x squared, and gx x dx. So if I consider the first term, I need to first evaluate this product at 1. Now what is f? Arctangent. times 1, and at 1 times g of x, which is the x function evaluated at 1 will be 1, minus f of 0, so arctangent of 0, times the gx at 0, which is 0, minus the integral of x over 1 plus x squared dx from 0 to 1. Now, what is arctangent of 1? Tangent of what? So that means we need to find the angle for tangent whose tangent value is 1, and their value, the angle to have 1 as the tangent value will be the quarter pi. So arctangent of 1 will be quarter pi, times 1 will be quarter pi. Now arctangent of 0 is 0, multiplied by 0 is definitely 0, so the second term is 0. Now when I look at this integral, I have x over 1 plus x squared. Now if you remember that when I differentiate 1 plus x squared, you get 2x, right? So if I put negative 1 half in front and then put 2 in the numerator, we get the same integral. And since this 2x is the derivative of 1 plus x squared, so the integral on the right hand side will be the log 1 plus x squared. If you differentiate this, you get 2x over 1 plus x squared. So I need to evaluate this function at 0 and 1. So I need to consider the quarter pi minus 1 half of ln. If I plug in 1 in place of x, then you get ln 2 minus, if I plug in 0, then you get ln 1. Now what is the value of ln 1? It is 0. So the answer will be quarter pi minus 1 half of ln 2, right? So that will be the answer for this integral problem. Okay, so let me go back. Okay, so as I said, we want to integrate this the arctangent, and at this point, what did I do? I considered the arctangent of x as the product of arctangent of x times 1. And then I considered this 1 as my g prime of x, while arctangent as f of x. Then everything is just the result of the integration by parts. And for this one will appear quite often, I mean, in your exercise problems. So what did I do? I multiplied 2 to the numerator and divided by 1 half by 2 to get the equality. And then this, using the fact that the derivative of 1 plus x squared is 2x. So please remember that ln f of x, given this function, the derivative is f prime of x over f of x. Actually, if this is not clear, then 1 over f of x, the derivative from the logarithmic function, and then by the chain rule, I need to multiply the derivative of this f of x. So if you have f prime of x over f of x, then you need to think of ln f of x. Okay, so that is one another example of the integration by parts. So the preceding examples show that the integration by parts allows us to express one integral in terms of a simpler one. And if the integrand contains a power of a function, okay, we can sometimes use integration by parts to reduce the power, meaning, okay, that means, okay, if I have any, as I said, a polynomial of x or a power of x multiplied by another function, and if your task is to integrate this product, then usually you need to put this polynomial f of x will be this polynomial. I mean, so in that case, this part will be f of x. Okay, and this another function will be interpreted as a g prime. So this is what people usually do. Okay, because as I said, if I consider this polynomial of x or power of x as my f of x, then what is the what are the terms on the right hand side in the integration by parts? You have f of x times g of x minus the integration of f prime of x times g of x dx. So f prime is given as the integrand. So that means the order, the power of x, it will be reduced by 1. Okay. So your the power of x will be reduced. Okay. If I apply the integration by parts. So that is okay, that will be called the reduction formula. But anyway, the point is that if you have any polynomial of x or power of x, then those will be your f of x in the integration by parts. Okay, actually finding the correct f of x, identification of f of x will be, I mean, if you do not identify the proper f of x, then the integration by parts will become complicated. Okay, so I will explain several patterns. Okay, so the first pattern in the integration by parts is that if you have any polynomial of x or power of x, then those will be your f of x. Okay, now in the example, we want to consider the following. We want to prove this formula. Okay, actually that is, if you see the exercise, we have similar problems for cosine and some other functions. Now, when I look at this number 7, the problem number 7, I have only a single term. I have some power of sine x, okay, instead of just x. Now, even in that case, we can use the integration by parts. First of all, I have one function in the integrand. And if I want to apply the integration by parts, then, as I said, I need two functions, but only one is given. Then what did I do in the previous example? I just considered that integrand as the integrand times 1, so that I can interpret that this integrand as a product of two functions. So if you see only one function, but if you believe that you need to apply the integration by parts, then you need to interpret that integrand as the integrand times number 1. So here, if I consider sine x to the nth by sine x to the nth power times 1, okay, then as I said, this will be f, and this will be your g prime. As I said, this 1 will be always interpreted as a g prime, not g of x. Then if this is f, then what will be f prime? Oops, just a second. Oh, I'm sorry. I made one mistake. Okay. Since this is the trigonometric functions, I cannot do this. I mean, because if I, okay, so the one mistake I made is this. I initially wanted to define f of x by sine x to the nth power and g prime of x by 1. Then when I consider f prime of x, then you get n times sine x to the m minus 1 times cosine x. That is f prime, and gx will be just x. Then, then, uh, okay, we can do this. Okay, this is not a problem. So if I do this, then and if I consider this by f of x times g prime of x, then given these f and g, f prime and g prime, the integration by parts tell you that f of x times g of x minus the integral of f prime of x times g of x dx. Then f of x is sine x to the n times gx is x minus f prime is n times sine x to the m minus 1 times cosine x times gx, which is x dx. Then the first term is simple, right? Simple product of two functions that is fine. The problem occurs with my new integrand. Sine x to the m minus 1 times cosine x times x. So the problem becomes more complicated. Okay, it does not become simpler. So that's why I made a mistake with f and g prime in this case. So my choice of f is not appropriate in this example. Okay, then how can I fix this? So this is not correct. I mean, this is not appropriate. So the next step is, okay, then I need to change f and g prime. Then how can I change this? Okay. In case of sine x to the nth, as I said, if I differentiate sine x to the n, you get, as I said, n times cosine x times this. N times sine x to the nth minus n times cosine x, right? And then due to 1, the problem becomes complicated. So what I can do is, since I have n copies of sine x, these n copies of sine x are multiplied all together, right? So I can put these n copies by n minus 1 copies times 1 copy. Okay. And then let me consider this 1 sine x as my g prime. And sine x to the m minus 1 by f. Then what is f prime? What is f prime? That will be n minus 1 times sine x to the m minus 2 times the derivative of sine, which is cosine x. Okay? And if sine x corresponds to g prime, what is g? Which function shall I differentiate to get sine x? You get negative sine, negative cosine. Then the integration by parts formula, oops, the integration by parts formula says that will be f of x times g of x minus the integration of f prime of x gx dx. So f of x is sine x to the m minus 1 times cosine the g of x, which is negative cosine x, minus integral of f prime, that is m minus 1 sine x to the m minus 2 cosine x, multiplied by g prime g of x, which is negative cosine x dx. Okay, so that will be, from the first term we get negative cosine x times sine x to the n minus 1. Now here I have n minus 1 times sine x to the n minus 2, and then I have one cosine, that one negative here and another negative sign here, so they will make plus sign, plus cosine squared. And since cosine x squared is 1 minus sine x squared, so if I put it this one here, 1 minus sine x squared dx, then I have negative cosine x times sine x to the n minus 1 plus n minus 1 times integral of sine x to the n minus 2 dx minus integral of sine x to the n minus 2 times sine x squared will make sine x to the n dx. Okay. So, and what am I doing here? I am integrating the sine x to the nth dx. I'm considering this integral. So I'm integrating this integral, and during the calculation, the same term appears on the left hand side. Okay. So I want to move this negative integral of sine x to the nth to the left hand side. Okay. Oops. Just a second. I forgot one term here. This n minus 1 must come here as well. So I have this term. Okay. And I want to move that term to the left hand side. Okay. So let me write down because I need some space. So I wanted to compute this term. The integration by parts shows that if you do the calculation, you get negative cosine x times sine x to the n minus 1 plus n minus 1 times sine x to the n minus 2 dx minus n minus 1 times sine x to the nth dx. That is the result of the integration by parts. So as I said, if I move this term to the left hand side, what do I get? I have n times sine x to the nth dx will be negative cosine x times sine x to the n minus 1 plus n minus 1 times the integral of sine x to the n minus 2 dx. Okay, so if I divide these terms by n, then this n will be cancelled, and you have this plus n minus 1 over n times the integration of sine x to the n minus 2. So those are these two terms here. So as I said in the beginning, the integration by parts, if you want to apply the integration by parts, the first step and the only step which is very important is to identify f of x and g prime of x. And as I did, you may find inappropriate function as your f of x. And in that case, the formula becomes more complicated, which was what I did. Okay, so what did I do? I fixed it. I modified f of x. Okay, so by doing this, you can find the correct result here. Okay, so that is the one examples of reduction formula. Okay. Now let's go to the second section 2, and we want to consider the integrals related with the trigonometric functions. So this section is quite difficult. Probably I will choose one problem in these sections. Okay, so please listen carefully. First, first, and actually, if you came from engineering departments, actually most of you came from engineering departments, and in that case, please listen carefully because in engineering departments, you frequently play with the Fourier series, Fourier sine series, or Fourier cosine series to make some signals and so on. And those are related with the integration of the product of sines or cosines. So please listen carefully. First, let me explain the theorem first, and then let me consider the examples. So first, if you want to integrate a product of some, excuse me, powers of sine x and some powers of cosine x. So if you want to integrate this shape, okay? Now, at this point, okay, sine x and cosine x, they have the same x here, okay? I mean, so the integrand is not, say, sine 2x multiplied by cosine 3x type. So in this product, the angles, okay, of sine and cosine are different. Okay. In this slide, okay, we are evaluating the integral of sine x to the mth power multiplied by cosine x to the nth power. Okay. So sine and cosine, they have the same angles. We have sine x times some copies of sine x times some copies of cosine x. Those are multiplied and this product defines an integrand. In that case, if in this case, you need to look at the values of m and n. Okay, if the power of cosine is odd number, in other words, what is the power of cosine? N. So if n is an odd number, then, so if n is 2k plus 1, you need to split this cosine as the product of cosine x to the 2kth power and cosine x. Okay? And then you replace this cosine x squared by 1 minus sine x squared. And then you substitute u, okay, for sine x. That's what you need to do. Now, if the powers of sine is odd, say if m is 2k plus 1, okay, then in a similar way, we split this sine x as a product of sine x to the 2kth power multiplied by sine x. And then you need to replace this sine x squared by 1 minus cosine x squared. And then you introduce u for cosine x. So if one of these two powers is an odd number, then the problem is simple. Okay? So, oh, if both numbers are odd, you can apply A or B. Either is, I mean, any, okay? Anyway, so if one of these two numbers, m or n, is an odd number, the problem is simple. You can just split that odd number as the even power times one copy. Okay? So here is an example. So if I have this problem here, I want to integrate sine x to the fifth power and cosine x squared. Then the power of sine is an odd number. So this sine x to the fifth is written as sine x to the fourth times sine x. And then this sine x to the fourth is interpreted by this, and then replace this sine x squared by 1 minus cosine x squared. Okay. And we do this because the power of sine x is an odd number. So sine x to the fifth is written as sine x to the fourth multiplied by single sine x. And then sine x squared is replaced by 1 minus cosine x squared. So if I expand this, you get 1 minus 2 cosine x squared plus cosine x squared times cosine x squared times sine x. So 1 times cosine x squared will be cosine x squared minus 2 times cosine x squared times cosine x squared will be cosine x to the fourth. And then I have cosine x to the fourth inside the curly braces. And then multiplied by cosine x squared will give you cosine x to the sixth times sine x. And then what is the next step? You replace this cosine x by u. So you introduce u for cosine x. So if I do that, so if u denotes the cosine x, then once you get this, you get, when you expand, you get cosine x squared minus 2 times cosine x to the fourth plus cosine x to the sixth, and those will be replaced by u squared minus 2u to the fourth plus u to the sixth. And so that handles this product of cosine functions. But what remains will be sine x times the dx. So here what I did was I introduced u to denote cosine x. So du dx will be negative sine x. So that means du will be negative sine x dx. Or in other words, negative du will be sine x times the dx. So this sine x times the dx will be replaced by negative du. Now the integrand now is a polynomial in u variable. So the integration is simple. U squared becomes 1/3 of u to the 3, and u to the fourth will be integrated to 1/5 times u to the fifth. And u to the sixth is integrated to become 1/7 times u to the seventh. So we get this. Once you get this form, that is not the final answer yet. So please note that this is not the final answer yet, because what is the problem? The problem is to find an antiderivative of this function in x. What I have now is certain expression in u. So you need to go back to these expressions in x. And since u is just cosine x, you can just plug in this for u, then you have some expressions in x plus the constant c. So that will be the final answer. Okay. So if I have some problem, okay, in x variable, your final answer must be certain expression in x. Okay. So if the problem is to find the antiderivative of certain function in x, and if what you have is certain function in u or t or s, that is not the final answer. You must go back to certain expression in x variable. So that is the formula for this product. If one of these two numbers is an odd number, what happens if both numbers are even? If both numbers are even, then please use the half angle formula. In other words, sine x squared is replaced by this, and cosine x squared will be replaced by this. So then why do I do this? We can reduce the power of sine and cosine to a single one. We have only cosine 2x. Even though the angle is doubled, the power of sine or cosine will be reduced by half. So if I have a problem like this, sine x squared, then you need to apply the half angle formula. Sine x squared must be replaced by 1/2 of 1 minus cosine 2x. Well, then the problem is simple, right? Right? So given 1, its antiderivative will be x. Given cosine 2x, the antiderivative will be half of sine 2x. Oh, at this point, so some students may forget this 1/2, so please be careful. So given this the integrand, if I just plug in 0 and pi and compute the difference, we can find the value of this. And in case of the definite integral, if you introduce a certain a dummy variable to for the sine x or cosine x, you don't have to go back to the original variable. Okay. Let me explain that concept with some examples. So if I have, so if my integrand is certain power of sine x times some power of cosine x, and if these two angles are the same, then definitely that will be, the integrand will be one of these three situations. So depending on the case, okay, you need to apply, excuse me, the appropriate formula. Now, if I have, if 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 I have, say, sine x, not sine and cosine, but some power of tangent and secant, we have similar formula. Okay, so let me tell you this formula first. So given this product as your integrand, and as I said, similarly to the sine and cosine, the angles are the same. Okay, not tangent 2x times secant 3x type. Okay, we have tangent x to the mth power multiplied by cosine x to the nth power. In, in that case, in that case, if the power of secant is even and that number, that this n is greater than, okay, or equal to 4. I mean, k is greater than equal to 2, so n is greater than or equal to 4. And it is even. In that case, you need to save a factor of secant x squared and use this formula to express the remaining factors in terms of tangent. I mean, given this secant x to the 2kth power, you rewrite this as secant x to the 2k minus 2 times secant x squared. Okay, and here, so given this secant x squared times, so secant x to the 2k minus 2 is the same as secant x to the k minus 1, and secant x squared should be replaced by 1 plus tangent x squared. So eventually you have tangent x to the mth power plus 1 plus tangent x squared to the k minus 1 multiplied by secant x squared. And then if you introduce u for tangent x, then tangent x to the mth will be u to the m multiplied by 1 plus u squared to the k minus 1. And then if u denotes tangent x, then du dx will be secant x squared. So du will be the same as secant x squared dx. Those product corresponds to du. Then the integrand is a polynomial in u. Okay, so the integration will be simple. So if the power of secant is even and it is greater than or equal to 4, the problem is simple. If the power of tangent is odd, say 2k plus 1 type, then save a factor of secant x tangent x, okay, and then use this formula to express all the functions in terms of secant x. So here I have tangent x to the mth power, and if this m is 2k plus 1, I have this. And then I have secant x to the nth power. So if I have such a situation, then you rewrite tangent x to the 2k plus 1 as tangent x to the 2k times tangent x. And then from this secant x to the nth, you take m minus first power times secant x. Then you get tangent x to the 2k. That means tangent x squared to the kth power multiplied by secant x to the m minus 1 times tangent x secant x. Now, what? So in that situation, if I substitute u for secant x, then du dx will be tangent x secant x. So du will be the same as secant x tangent x dx. So this will be your du. And tangent x squared will be replaced by secant x squared minus 1. So the problem becomes u squared minus 1 to the kth power times secant x to the m minus 1, that is u to the m minus 1 du. So I have a polynomial in u again, and then you can integrate this function within u, okay? And then once you have a function in u variable, that is not the final step, and then you need to plug in secant x for u, then you get a function in x variable. So that is that is the formula when the power of tangent is an odd number. Okay, the formula A considers the case when the power of secant is even. Okay, and in formula B, if the power of a tangent is odd, then we have a certain formula. But what if these both are not satisfied? For the other cases, the guidelines are not as clear cut, and you may need to use identities, integration by parts, or occasionally certain other formula. Okay, so if the integrand is tangent x to the mth times secant x to the nth, in that case, if you are lucky, and in the sense that if the conditions for A or B is satisfied, then we can we can use this trick. Otherwise, we don't know. In that so otherwise we do not know how to handle. There is no one guideline. You need to apply several ideas, such as some identities, trigonometric identities, or you can apply the integration by parts, or okay, and so on. As an example, if I have this, okay, so if the power of secant is even, okay, so the power of secant is even and greater than or equal to 4, then what do I need to do? You need to separate secant x squared. So you rewrite this secant x to the fourth by secant x squared times secant x squared. And then first the secant x squared will be replaced by 1 plus tangent x squared. And then the secant x squared dx will be the derivative of tangent x. So we have secant x squared dx, and that will be du if u introduces u is for tangent x. So tangent x to the 6 will be u to the 6 multiplied by 1 plus tangent x squared, which is u squared. And then secant x squared dx will be du. So I need to integrate u to the 6 plus u to the 8th du. Okay. Then u to the 6 is integrated to 1 over 7th times u to the 7 plus 1 over 9th times u to the 9th. But as I said, that's not the final answer because I'm asking you to find this, which is expecting certain function in x variable. Now, what I have now is some expression in u variable. So you must go back to a certain expression in x. But since u is introduced to represent the tangent x, I can just go back to some expression in x by replacing this u by tangent. So that will be the final answer for this problem. Okay. Oh, then before I go to the next one, let us consider a few examples. So sometimes I need to integrate tangent x, but that is a simple because tangent is sine x over cosine x, and and the derivative of cosine is negative sine. Okay, so 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 here the derivative of cosine is negative sine. So if I integrate this function negative sine x over cosine x with respect to x, then you get ln cosine x. Okay, and since I have this negative sign, that is which is the reciprocal of cosine is secant. So if I integrate tangent x, then you get ln secant. And in case of the integration of secant, oh, here is the answer. So secant x is the same as secant x times this one. That is the value 1 because the numerator and denominator are the same. Then we get secant x squared plus tangent x secant x over secant x plus tangent x dx. Now, if I differentiate tangent, you get secant x squared. If I differentiate secant, you get tangent x plus secant x, right? So that means if I differentiate the denominator, you get the numerator. So the antiderivative, the integral will be this. Anyway, thank you for listening, and let's take a break for 15 minutes and see you in 15 minutes.